Ever gone traveling and seen something and thought to yourself, how did that happen? Maybe you're in a national park, maybe you're hiking in the woods, maybe you're driving down the highway, maybe you just see a cool rock formation somewhere. Maybe it's something simple like how a river formed, or why there's a big rock in the middle of a field. Well, I'm a wild geo dude, and hopefully I have some answers. Over the years, friends and family have been asking me loads of questions about just random geology stuff. So I thought, maybe you have those same questions. So I'm going to try to start answering them. Maybe you've had these questions yourself and have Googled them. Maybe the YouTube algorithm has brought you down this 3 a.m. rabbit hole. Regardless of how you got here, this is a video. Let's see if I can answer something. Mount Monadnock is a mountain in southwestern New Hampshire in the US. It's about 3,165 feet above sea level, but only about 2,195 feet in prominence. What that means is it only looks like it's about 2,000 feet tall, or it's actually, a little over 3,000. It also happens to be the most hiked mountain in the entire country. About 150,000 people hike it each year. In the world, it's second only to Mount Fuji in Japan, although China's Taishan claims to have 2 million people hike it each year. Statistics are debatable, but the point is, a lot of people hike this mountain. So in the US, freestanding, erosion-resistant mountain is called the Monadnock, named after this big pile of nut. In this context, freestanding just means it's not part of a greater mountain range. So you have the Green Mountains in Vermont, off to my left, over behind the camera, to the west. You have the Appalachian Trail, the Appalachian Mountains. The White Mountains are northeast of us by about 2 hours, 2-hour drive at least. And then back over there, hopefully you can see it, that's Mount Wachusett. It's a little ski resort, not really a resort, just a ski mountain. I went there growing up a couple times. Nice spot. Also, a Monadnock. So here's the question you may be asking yourself. Why is Mount Monadnock all by itself? Why is it the way it is? Ever heard of it? No? Good. Maybe you'll learn about a cool new place. If you thought of the question, no? Maybe you'll realize that you actually did wonder why it's all by itself. If you answered yes to any of those questions, strap in, because I'm about to learn you a thing or two. The story of Monadnock started about 415 million years ago. The east coast of the US was part of an ancient continent known as Laurentia. It's also known as a paleocontinent because geologists love to throw paleo in front of anything and everything they can. There are 2 other paleocontinents that you need to know about for this story: Baltica and Avalonia. Now at this point, the area that would become New England, and therefore New Hampshire, was underwater off the coast of Laurentia, just hanging out, collecting all the sediments that were eroding off the continents and getting deposited over time. Around about 390 million years ago, the tectonic plates brought the 3 continents closer and closer together until they collided around 335 million years ago at the equator. This formed what is known as the Caledonian orogeny. And as a side note, an orogeny is just the formation of a mountain range. An important thing to note is that a mountain range is a lot like an iceberg. The rock goes up, and the rock also goes down. The Caledonian orogeny and the mountains were some of the tallest the world has ever seen, and what we know as the Appalachian Mountains are actually the remnants of this ancient mountain range. The roots of the mountain kept going down, and as they did, the intense heat and pressure turned them into metamorphic rocks. On a similar note, the hotter rocks get, the more malleable they get. That is correct. Rocks actually do get soft, kind of like a Play-Doh consistency if the conditions are correct. We call this plastic deformation. The roots of the mountains folded from all of the compression and formed what is called a syncline. More on that later. Now at 175 million years, Pangaea has already formed and is already separating, again, through tectonic shift, and the Caledonian Mountains are eroding. And this is where it starts to get interesting. Fast forward to just 5 million years ago, the Earth looks pretty much exactly as it does now, and the world is covered by glaciers because of the Ice Age, or at least one of the many ice ages. As the glaciers advance, they pick up rocks, boulders, and pretty much anything they can, and these sediments get dragged and ground across the existing bedrock, including the mountain itself. And you can still see the evidence of this today, known as glacial striations, and they can tell us what direction the glaciers moved. In Monadnock's case, it is a north and south movement. 15,000 years ago, the glaciers began to retreat and actually changed the shape of the mountain. It's now offset in the same directions as the striations. Kind of like the Mount Crumpet shape from the Grinch, but not nearly as dramatic. The northern side of the mountain has a more gradual slope, while the southern side is steeper. Alright, so hold on. I explained how Mount Monadnock formed, but I never actually explained why it's all by itself. And I also mentioned that syncline earlier, but never explained what that is. Here's a little explanation. So, the mountain is primarily made up of two types of rock, schist and quartzite. Metamorphic rocks are naturally harder and erode slower than the sedimentary rocks that were sitting on top of them. So as the mountains were shrinking, the exposed schist and quartzite stayed where they were while everything else eroded around it. So, this is a pretty good example of some of the schist on top of the mountain. This is what's called a mica schist, and hopefully you can see it, but because of the sun, you can see all these little sparkly bits right here. That's the mica. So mica is a mineral that forms little layers, not layers, like flakes, and we call them foliations in a metamorphic rock when it looks like a layer, but it's not. So with a mica schist, a schist forms from something like a siltstone or a mudstone, shale, something similar to that. And the mica appears when it undergoes, the metamorphic process, so heat and pressure over time. Whatever minerals are already present in the mudstone, shale, whatever, those are converted into mica. And when there's a lot of mica in it, you call it a mica schist. And mica, and along with some of the other minerals in there, are what are called index minerals. So what that means is that the index minerals form under certain conditions, so a certain pressure, a certain temperature, and they allow us to figure out what depth the rocks, were at one point. Pretty cool, right? The other main rock type is called quartzite. This can get a little tricky in conversation because sometimes a pure quartz sandstone is also called quartzite. The fun part is that a metamorphic quartzite is actually formed from a quartz sandstone. So to differentiate, we usually call the two orthoquartzite, which is the sedimentary type, and then metaquartzite, metamorphic quartz. Metamorphic quartzite. It's all a tongue twister. So this is the metamorphic quartzite. You can tell because at first glance it just looks like, big quartz crystals that are kind of weirdly wavy, but then as you get closer, it's not going to zoom in well. You can actually see little grains of quartz within this. And up here you have a slightly different type, and it looks just like lichen. Yeah, it's lichen. Quartzite. There's another bit right there. One way you can tell you're looking at, the metaquartzite as opposed to the schist. See this edge right here? It's a little rounded. Quartzite tends to do that when it's weathered, especially by glacier. Schist can do it, but it's a little clearer with the metaquartzite, which like I just said, came from a quartz sandstone. So it weathers slightly easier than schist. Still metamorphic, so it's harder, weathers less easily. But it's all kind of relative. The big index mineral, though, is called sillimanite. This can form at a range of temperatures and pressures, but an easy way to think of it is at pressures of around 3 kilobars and temperatures around 500 degrees Celsius or 1,000 freedom units. But what is a kilobar? Kilobar is just a way of measuring pressure, and it's equal to 1,000 bars. Now, with no explanation, that means nothing, but for context, the air pressure at sea level is about 1 bar. So sillimanite requires 3,000 times that much pressure, as well as an insane amount of heat in order to form. This is a great example of sillimanite because you can see, right here, you see lines going this direction. Those are the mineral layers within the schist, but then you have all these big crystals that are angled and they're sticking out, especially this one right here. This one is really good. This happens because the sillimanite is a harder material than the rest of the surrounding rock. I said this is a mica schist. Sillimanite is a harder material, so when everything gets weathered or scraped away or weathered, however it happens, in this case it was a glacier or people walking, this is hardier, so it doesn't weather as easily, which means it sticks out. Pretty cool, huh? So this is all sillimanite. This formation is called turkey tracks because it looks like a bunch of turkeys just walked across the rock and left all these tracks. All right, here's some examples of those glacial striations I just mentioned. So see, this line and that line, all these tiny, I'll zoom in, get a little closer, all these tiny grooves that go all the way this way and they extend that way. You can see them all over the peak. I'm a little down past the summit right now. Those are the glacial striations. Those are caused by little, chunks of rock, boulders, gravel, just whatever the glaciers picked up, and they are dragged all along the surface of the mountain, the rock, anywhere there's exposed rock, and they cause these grooves. These are glacial striations. All right, now this is really cool. This is called a Billings Fold, and it's named after two geologists that lived and worked in the Monadnock region. I'm not sure when, I haven't found a source for that. Called Catherine Fowler Billings and Marlin Billings. Basically what this is, same as the entire mountain, this fold occurred when the rocks in the larger syncline that formed the mountain heated up, were under pressure, compressional forces pushed them together, and they underwent plastic deformation, and you get a smaller fold. For the scale, I don't know if you can tell how big that is. Check this out. Pretty big. For reference, I stick my arms out like this. I am about a 2 meter square, so that's a good sense of scale.